understand.
Check.
Houston recovery, Hornet recovery. I read you loud and clear. Have you confirmed command module, service module separation? Over. Roger,
Okay,
Hornet
I'm hearing
recovery. We
myself,
confirm
so I'm going to
that,
pipe this down. And I'm hearing myself really nice.
Pass it out to Mel. Over.
So your levels,
Roger,
so
understand. I'm up
here
on
is like
the
mic
up on the
level,
ship's bridge
Hornet
right
level
now.
probably
I've
around
just
here.
finished briefing the president,
The only thing is, yeah, so what's
and,
going
he's
in
out
is
on the
not
port
that
wing of
hot.
the
So I could
flag
bump
bridge
up this
immediately
to get a
below me
better
here.
signal coming in.
Looks like
But
it's
is
pretty
that
well
distorting
clogged up
now?
out here. I doubt very much if we get to see anything.
How about now?
As far as
Yeah,
heat
so
state
this
and
might
winds are
be,
not bad. It's
as long
simply
as it's
the
not
high
distorting.
cloud cover, and I
But
doubt
then,
that we're going to get to.
and so, yeah, we are live right now. We've been live, but no one knows. Actually, we got to update the website. But anyways, Check, test.
That's a good one.
Houston, recap.
How's this live?
Are we good?
Mix one. Mix one was. We're not worrying about this. Sorry. Okay, this level's good. Nothing on 10. Nothing on 9 was good.
That's correct.
First catch was
8.
catch mark was 8.
And 7 is microphone judge. That's right. 1 is the podium. Which one? I fixed it. They're all good.
Like someone's gonna look and say, oh,
No, I'll double check, but I think I got 60. How close are we? Alright, well I can give Rick a thumbs up.
yeah, it sure is. Okay. Folks, we're about to start the NASA portion of the program, so if you'd like to grab a seat. And we welcome both our NASA Exploration Science Forum attendees as well as the public, so please join us.
Mike Seppin doesn't seem to be.
You mean the last?
Yeah, the one closest to us.
This guy's live?
Yes.
All right, let's go ahead and get started. My name is Greg Schmidt. I'm director of the Solar System Exploration Research Virtual Institute based at NASA's Ames Research Center, about an hour drive south of here, or maybe more like 3 hours in rush hour. And we are just so honored to be spending the 50th anniversary of the Apollo 11 landing on board the ship that picked up the crew. What an amazing honor that it is. I want to start off by thanking Captain McCarran and Laura Fees for their kindness and working with us for several months to make all of this happen. So, Captain McCarran. So we have a special program for you today, and we're going to start off. I will make an introduction in just a second. We're going to start off by a panel on lunar geology, past, present, and future. Then we have a special surprise event that I'll tell you about when this panel is over. That's going to be just a few minutes. And then we're very privileged to have 3 leaders from NASA to be talking about our future plans to go to the moon. We figured it was appropriate. We're looking back 50 years. Well, let's look ahead as well. NASA has some pretty exciting plans. So with that, I'm honored to introduce Dr. Jacob Bleacher, who is the Chief Scientist for the Human Exploration and Operations Mission Directorate at NASA headquarters. So, Jake.
So this is quite an event, I'll say. I'm very excited to be here. I think all of our panelists, myself, many of you in the audience and maybe listening online have spent a large part of the last week, several weeks, telling stories about Apollo, listening to stories about Apollo as we head into this anniversary. I think it's a fair claim to state that the Apollo missions to the moon are among the most amazing stories ever told. But they're not just a story of a launch or a landing, it's also a story of a return to Earth, a splashdown in the Pacific Ocean, and this ship, rescuing and bringing back our crew members and our rocks, the samples that they brought along. It's also a story of individuals, of a nation, of humankind. And I hope that this panel will demonstrate that it's a story that's not actually done yet. It's a story that we're going to continue to tell. It maybe started with Apollo, but we're going to keep going. And so that's where we are today. And so I'd like to introduce our panel to you. Down on the left is Ariel Deutsch. She's a PhD candidate at Brown University. She's a NASA graduate fellow at the Goddard Space Flight Center. She studies processes related to volatiles, volcanism, impact cratering on the moon, and she represents the next generation of researchers who will support the efforts to place our astronauts on the moon by 2024. Beside her is Jennifer Heldmann. She's a research scientist for NASA's Ames Research Center, has served as a director for Survey's Field Investigations to enable solar system science and exploration, or FINESS. She's also now leading a new survey team, Resource Exploration and Science of our Cosmic Environment, or RESOURCE. Jen has been involved in bridging research and exploration goals between the moon and Mars, including a focus on understanding the role that volatiles play as a resource for astronauts as they explore our solar system. Beside Jen is David Kring, and he serves as a principal scientist at the Lunar and Planetary Institute in Houston. He also serves as the director for Survey's Center for Lunar Science and Exploration. David studies processes related to impact crater development and evolution on the Earth, Moon, and planets. In addition to his research focus, he's led many field training exercises to help develop the next generation of planetary scientists, as well as to help train our astronauts. And he applies his research to help develop the human exploration architectures that will help return us to the moon. Beside him is Jack Schmidt. He's a research scientist, he's a geologist, he served as a US Senator. He's also a crew member of Apollo 17, and he walked on the surface of the moon. But he wasn't only an Apollo 17 crew member. During Apollo 11 EVA, he served as a Capcom support, thereby ensuring that science had a voice during this momentous occasion. His role with lunar research did not end in Apollo. Jack has served as a powerful advocate for lunar science and human exploration. He also serves as a mentor to many of us here, and the work that he does will help us also return humans to the moon. Now I'll go ahead and get this started off, but really we want to hear the questions that the crowd has. So hopefully this will be engaging, we'd like to hear again from our panel about how we're going to continue to tell this story about exploring the moon and beyond. So just to get started, I'd like to go ahead and ask the panel members to just give a brief story or favorite memory, Apollo 11, and what it really means to them to be in the positions they are today. So Ariel, maybe we'll start with you.
I wish I had a favorite Apollo memory to share. But I think that the Apollo program is the true epitome of exploration, and it's that discovery aspect that really inspired me to become part of this community. And I think it's really clear this week that the impact that the Apollo program had was very powerful and inspirational, emotional, and it was felt worldwide. But I didn't experience it, and I don't think a lot of people in this room had the opportunity to experience it. And you asked us to think a little bit about one of our favorite images of Apollo, and I kind of went back and forth with all of the images of astronauts on the moon, and you're looking out on this vast landscape, and those always get me, but one of my favorite images is actually back on Earth in Mission Control, where people are really looking at the first time that man stepped on another planet, and the inspiration, the excitement in those faces is really, I think, cool, and that's something that I want to be a part of. And the other thing about those faces is that they're all very young, and we heard a little bit about that just before. The people involved in the Apollo mission were in their 20s and in their early 30s, and so as a young person entering the field, I think that's really inspirational and can't wait to be part of continuing that legacy.
So, right, similar to Ariel, I was not born yet during Apollo, even when Apollo landed. But I feel that I owe most of my career to what Apollo accomplished, because that's, when I thought of Jake's question, he asked us earlier, it was inspiration. Because now we know when people like Jack, which by the way, if you ever work at NASA, which I hope many of you do, because there are many young people in the audience, I feel that this is one of the occupational hazards. Or you can go to the tour. 3:15 if you'd like to leave. But please stay. But it's an occupational hazard of working at NASA because astronauts are the coolest people on the planet, well, and off. And then on occasion, if you work for NASA, you end up on a panel with astronauts. And then you end up in a panel with an Apollo astronaut, and that's like the top of the top. So I'm very honored to even be here today. But it's the inspiration, because as Jake had mentioned before, what I've worked towards, and many other people at NASA and people that work with NASA, is having a sustained human presence out in space. And so just by virtue of the Apollo program happening, we know that that is possible, that we can do that. We can send people to other planetary surfaces. And so it becomes something that's tangible that we know we can do. And so the work that I've been doing, and many, many others in this room and elsewhere, is looking how can we make this sustainable. So I've focused a lot of my research on looking at water and ices and volatiles in the solar system with an eye towards both the science and also towards using that water as a resource. In situ resource utilization, living off the land, so to speak. When you go to explore, you use the resources that are there. And water is a very valuable resource. You know, you can drink it and you can brush your teeth, but water is H2O, so you can break it apart, and that's hydrogen and oxygen, and that's how you make fuel or propellants. And so that gives you a lot of capabilities to have a sustained presence. So that's one of the very exciting things. And then just to emphasize what Ariel said, you know, for the early career folks, and even in high school and middle school, you're the ones that will be making this happen. You will be the ones that will be sending people out for longer periods of time. So we're trying to help you and lay the groundwork so that you can do that. And I just have one quick story, because I feel like the future is happening now, and the future that we want to see is happening now. Because a couple weeks ago, I said to my 8-year-old daughter, I said, you know, NASA's gonna send a girl to the South Pole of the moon in 2024. And she just looked at me like I was really dumb. And she said, well, NASA's already sent people to the moon, so they've already sent girls, so what's the big deal? And I was like, and I was dumbfounded, and I didn't even know how to respond. And so I didn't. And she just went back to doing whatever she was doing. And then I thought about it, though, and I thought, this is fantastic, because she's growing up in a world where she doesn't see the limitations. She doesn't see that, you know, girls can do this or boys can do this or any gender identity. It doesn't matter. If you're a person and you want to do something, then you go and do it. And so I feel like we are starting to see that become a reality, and so I think that's also a bright point for the future of human exploration.
If I had to choose a word, it would be, as Jen said, inspiration when Apollo 11 happened. And I am old enough to have seen it. It was a treasured moment in my life, as I think it was for most people in my generation. The minute you saw the astronauts land on the surface and return safely to Earth, anything was possible. I mean, literally anything was possible. For me, what I wanted to make possible is be a planetary scientist. And I say that, but those words, by the way, didn't even exist at that time. There was no planetary science department. And so you did have to figure out, you had to navigate a way into the profession. But one of the things that I remember is having a tremendous number of mentors, and that's something I'll never forget. For me, it was Basu at Indiana, Gordon McKay and David McKay at JSC, Ursula Marvin and John Wood at Harvard, where I went to school, and other people in the field like Jack. So Jack won't remember this, But when I got my PhD from Harvard and got my
Are you
first...
saying that I'm too old to remember things?
No, it's just because you're one of these people who does so many things for so many people, you can't possibly keep track of all of them. So I get my first posting at the University of Arizona, and I'm sitting in my office one day and somebody walks in with my mail, and there's a letter from Jack Schmidt. And he says, I understand that you have a new post at University of Arizona. And he sent me a reprint about some Apollo finding that you had. I have to admit, I don't recall, but I still have it. He had some remarks on that cover. It's like, there's all these people, as a young person trying to gain a foothold in the profession, that were a positive influence, right? So I'm now at the end of my career, or getting close to the end of my career, and I try to do the same thing. Don't laugh, Penny.
She was laughing at me because I looked askance.
Yeah. You're a special person, Jack. I won't have your energy at your age. But so I'm absolutely thrilled that I've had an opportunity, as Jake said, to train astronauts and train graduate students, undergraduates, high school students, undergraduate students, graduate students, and postdocs. And I probably have another 10, 15, maybe 20 years to do that. And what I would like to give them is the one thing I have to say my mentors failed to give me, and that was an opportunity to be part of a lunar mission. I really hope we pull this 2024 thing off. I know I am working day and night. It's so important because I want to go back to that word that I started with. Apollo 11 was inspiration. It inspired everybody in this country. Anybody could do anything. And I'd like to give the new generation that very same feeling.
I hope somebody will ask me later about why did we fly the experiments we flew on Apollo 11. But I want to talk a little bit about the origin of the selection, the landing site selection for Apollo 11. It goes all the way back to Apollo 8. As many of you are aware, we had, for the early Apollo missions, we had sites identified across the equatorial belt of the moon that were spaced with about a 2-day delay in the launch window from Florida. And Apollo 8 was targeted to the easternmost of these sites, which had been characterized to the best of our ability using the photography available at the time. That included some pretty good lunar orbiter photography. After Apollo 8, the crew came back, and particularly Bill Anders, and he said, you know, we looked very carefully. We had a 10-power monocular on board. Looked very carefully from 60 nautical miles at the easternmost landing site to which we were targeted, and it looked pretty good based on what we could see. And this triggered in my mind, said, well, now let's see, we've got 2 days between landing sites. Why don't we get the same good feeling about, if we can, about the next 2 landing sites? So I went to Tom Stafford and said, Tom, is it okay if I work on delaying your launch day, turns out by 1 day, so that we can, so that you all can look at those next 2 landing sites, because they were going to be in orbit long enough to see 2 more landing sites. What did that mean? That meant that if you targeted Apollo 11 to the easternmost site, then if there was a reason why you didn't launch, you had 2 more choices that we had really looked at, even though it was from a fairly high altitude. And he said, go ahead, see what you can do. And so I began to carry out one of my little lobbying campaigns, which you could do in those days. Decisions were made very quickly. And once I had all the view graphs, everybody remember what a view graph is? There you go. Had all the view graphs prepared. The first major manager that I went to was the now unfortunately late Chris Kraft. And Chris had a little meeting in his office with some of his senior managers. And I made the presentation, and Chris was looking very skeptical. And then suddenly the lead recovery officer, Jerry Hammock, jumped out of his chair and he said, "You mean you can do all of that and we get a daylight landing too?" People forget Apollo 8 landed in the dark. And that was not good. Jerry did not like to have his splashdowns in the dark. And so that sort of persuaded Chris that maybe that was something worth thinking about. And we gradually moved it up. Gradually meant the next day we made our briefing to George Lowe, who was the Apollo spacecraft program manager. And George was also very skeptical, because what it meant was that they couldn't use, if they delayed the launch of Apollo 10 by a day, they couldn't use what they call the data pack for the mission that they had already prepared for Apollo 8, and they would just need to modify a little bit. And so he was quite skeptical because of that. But it turned out that the Apollo program manager, Sam Phillips, was in the, General Sam Phillips was in the office that night. By the way, this briefing took place about 10 o'clock at night. And we worked till 10 o'clock at night in those days. Sam was there, and he didn't say a word, but the next morning, Tom Stafford called me and said, "Jack, you sold it. We're going to launch on the 17th of May instead of the 16th, or maybe it was the 18th instead of the 17th. And that is what finally determined the Apollo 11 landing site, because by God, they weren't going to redo the data pack again. And so they used the Apollo 10 data pack, and that was Tranquility Base. So now you know why we landed at Tranquility Base. Look forward to your questions.
Okay, I'm going to start out with one question, and then we'll have about 30 minutes for unless we talk really long, then maybe a little less, but hopefully we'll have about 30 minutes for questions. Many of us who study the moon often use phrases, for instance, that the moon is the key to understanding the solar system, or it's the test bed to understanding the solar system. So I just was wondering from each of you if you could maybe share with us how the moon and the samples and the observations of the moon help us understand the solar system and our place in the solar system a little bit. Jack, maybe we can start with you on this one.
I'll go quickly, because I mentioned this morning that once we had the samples back from Apollo 11, it was very clear the moon was a very old body. It recorded the history of the solar system. Yeah, at least the early part of that history very well, and that history was extraordinarily violent. And that included violence here on Earth, the violence created by very large impact basin formation. And if you've made quite a number of these on the moon, you made even more here on Earth. And so that characterized the early history of the Earth, probably the first 800 million years or so. And it was also a time in which complex organic molecules were getting organized. And one of the puzzles that I think we need to work out is, how did that all work out? Why did we have that organization occurring at the same time that the Earth's environment was extremely violent? I think there's some potential hypotheses that need to be examined, but it is, I think, a very important part of why we went to the moon. In fact, I would characterize that as probably the most important knowledge about the Earth that we've gained from the moon, was this period of violence in its early history.
Not surprising, there's going to be some overlap with my answer with that Jack just gave. And I actually have a slide. I think I used it over a year and a half ago in the Webb Auditorium at NASA headquarters. I think it captures this. It's the big ideas that I think came out of Apollo, and it's all generated by the samples. And they are the giant impact hypothesis for the origin of the Earth-Moon system, the lunar magma ocean hypothesis. You know, the moon was a differentiated planet, not an asteroid like Harold C. Urey thought. What was then called the lunar cataclysm hypothesis, we now think of as the inner solar system hypothesis, and we do debate the magnitude and duration of the late heavy bombardment, but certainly, as Jack said, there was an intense period of bombardment in the first billion years. That feeds into the impact origin of life hypothesis, this juxtaposition of the end of the basin forming epoch and the rise of life on planet Earth and potentially Mars. The magmatic epoch hypothesis, this new notion that the South Pole Aitken Basin may have caused an intense period of magmatism on the near side. And the most recent one, because we are still teasing things out of the samples, is the story of Earth's, of the moon's water and the origin of water in the Earth-Moon system. And that then has this fascinating twist into exploration, which I'll leave to Jen to talk about, but it's that we might actually utilize this for exploration.
Thanks for the segue, David. Yeah, so as something that Jake said in the introduction, Apollo really started this renaissance in lunar science, and it's still going on. The story is still being untold, and we're still trying to figure out some of these mysteries. So as David mentioned, we have samples back from Apollo that were very dry, right? There weren't flowing rivers on the moon, there weren't oceans of water, there's no sandstones, there's no shales, there's no limestones, none of those signatures of water. So when I grew up, we were told the moon is very dry, the moon is bone dry, thank you very much, moving on. But then it was about, we got these samples, and then about 20 years ago, some more missions were being sent, Lunar Prospector was sent, people in this room worked on that. I'm looking at you, Rick Elphick. Right, and found these interesting signatures of hydrogen, particularly near the poles of the moon. And usually that can be a proxy for water. So why would there be enhanced hydrogen near the moon? And so this was very intriguing to NASA and to the science community, also for the exploration side. And so we've sent some follow-up missions. NASA Ames led a mission about a decade ago where we intentionally crashed the upper stage of a launch vehicle into a permanently shadowed region on the moon. So there are places near the poles of the moon, just because of the geometry and the way the sunlight's coming in near the poles, that have not seen sunlight for billions of years. Billions. Very, very cold, like 40 Kelvin, like colder than Pluto, extremely cold. So we call these cold traps because basically ices or volatiles, they get delivered there maybe by comets, maybe by asteroids, part of this bigger picture of where did this water come from in the inner solar system. And the water and ices can't get out, it's too cold, so they get cold trapped and they're stuck there. So we went and we impacted and kicked up a big plume of ice, dust, debris, and lo and behold, there was about 5.5% weight water there. Like there was water there in a usable amount for exploration. And so now NASA is taking the next steps to say, okay, we need to ground truth this water. We need to really figure out this story. Where is it? What form is it? How deep is it? How is it distributed? And then can we use it? Can we use it for sustained human exploration? So it's a really nice segue, these decades-long stories of lunar science that we're still working on today, and really at the intersection of both science and exploration. So these are some of the exciting things that are happening.
Yeah, to build off that, I think one of the really great things about Apollo is that it not only addressed these interesting science questions, but it enabled us to ask even more detailed and better science questions that we're still asking today. And so, for example, thinking about the whole water story, we didn't really understand how the moon formed, and then if it was such a catastrophic formation, what that meant for water being retained. And so when the Apollo samples came back, and one of the professors at Brown, Alberto Saul, was able to actually find water in these volcanic glasses, that's actually one thing that's driven my own research and interest in being able to be part of this field. But I think overall what's really fascinating to think about is all the major questions that we're interested in, both the formation of the moon and the evolution of the moon, ties back to all of our big picture questions about Earth and the solar system as a whole. How did we get here? How did life form? How did our planet come to be? And I think that's why it's really important that we continue to explore the moon going forward.
All right, thanks very much for that. So with that, maybe I'll stop asking questions and go to the audience. Go ahead. Do we have a... Nope, here we go. If you go ahead and ask your question, I'll try to repeat it. That way we make sure we can hear it online, and then we'll go ahead to the...
Oh, thank you so much for the opportunity today. Jack, when you were prospecting on the lunar surface, did you sense that anything was not according to your training and your perception just by walking around, or did it all look like what you expected it to see from what evolved scientifically from the result of that mission?
So the question is whether or not, when Jack was on the surface of the moon, he noticed anything that was not quite to the way he was trained to perceive the surface. Jack?
Just about everything that had a geological context to it was new. Our identifying resolution in the planning for the Apollo 17 mission was probably about 15 meters, something like that. So everything that we were seeing inside of that was new. And believe me, there was a lot that was new. Not only the discovery of the volcanic ashes at Shorty Crater, but it turns out we have at least 2 samples that I think came from the deep mantle of the upper mantle of the moon, say 400 or 500 kilometers down. That's based on textures that I was familiar with from my work in Norway. I didn't see them on the moon, but later on we've seen them here in the laboratory. Also, I think we found evidence in sampling both the North Massif and the South Massif regolith, excuse me, that there were pre-Mare pyroclastic eruptions. They were actually probably lithoclastic eruptions of debris that was entrained in early evolved volatiles prior to Mare melting and entrained out of the megaregolith of the crust of the moon. I think we have good evidence that that occurred. So you can see that each station tended to have something new and interesting, particularly in the context of the analysis of the samples once they were brought back to Earth. And that's very important to realize. It'll be some time, I think, before we have the analytical techniques on the moon that will enable us to do the kind of very detailed, deep dive research that can be done here on Earth. Someday that probably will happen. Someday we'll have settlements on the moon and laboratories that will be able to do that work in situ, so to speak. But for a while, and I think certainly in the next decade or so, that's going to have to be done with return samples. I might also mention that in the context of the water that has now pretty well been documented at the poles, with the Apollo 11 samples, we also documented that you can make water anywhere on the moon. Now you have to heat the regolith in order to get the hydrogen, the solar wind hydrogen, to react with the minerals that are there. But our estimates at the University of Wisconsin have been at about 600 or 700 degrees C, about a third of the hydrogen will come off as water. And so you have to play that into your thinking about long-term exploration of the moon and where you might put a settlement and what the cost trade-offs are and so forth. That, I think, is a very important thing for people to remember and keep in the back of their mind, even though it looks like the target for 2024 is going to be in the areas of permanent shadow, namely at the South Pole.
Maybe an extension of that question. I know David and Jen, you've both worked with training folks in the field. How do you prepare people for the unknown when you're training in that regard?
Well, a
lot of field geological experience.
Yeah. So, yeah, Jack said it exactly right. And my number one training objective is to teach the astronauts how to observe and to communicate what they're observing to people in Flight Control Mission Ops Center. And they actually do that naturally very well. It's part of the selection process. I don't know if it is a particular element of the selection process, but astronauts by and large are brilliant people. If you don't know that. They are truly brilliant people. They're very good at observing things and very quickly making deductions that are correct. And as long as they can communicate in a language that the people in the flight control rooms can understand, you can make a huge amount of progress. Now, you have to introduce them to the right terrains. And for 2024, the thing that I tried to point out yesterday, it is nothing but an impact cratered terrain. And so we need to introduce them to impact cratering geology and how to work in that type of environment. And we did that during Apollo. We'll be able to do it again.
Yeah, I think it's exactly what Jack said, field geology experience. You have to get out in the field and actually see the types of scientific features that you're looking for and how to interpret them. And so we've been lucky through several projects. We'll bring folks from the astronaut office, from NASA, from CSA, et cetera, into the field. Barbara Cohen led one of these to an impact structure up in northern Canada that hasn't been visited in decades, and now I know why, because it's really hard to get to. But so we do this, we bring the astronauts out, and one of the nice things, like David said, these are really smart people. And so what we've been doing is also not just having them do the field science, go out and do the field work, that's part of it, but then also being involved in the analysis afterwards. What happens to those samples when you bring them back into the lab? And so they have an appreciation and an understanding, because not every astronaut is a bona fide field geologist like Jack, right? And so they get really into it, and then they understand, okay, this is why we're doing this. These are the questions you're asking. These are the features you're looking for in the field, and this is why you need it, because when you take this back into the lab and you do your geochronology or your analysis, these are the features that you need. It's not always just the shiny rock over there that you want, but you need to be able to do the high grading, because you can't bring back every sample that you want. That's true from remote places on Earth. We often go to, we call analog features, places on Earth that have characteristics similar to where you'd be going on another planetary body. So you work within those same constraints and really teach them how to do that, have an appreciation for it, and have them be involved in the whole process while gaining that experience along the way.
Ariel, do you have any thoughts?
Well, I think what's interesting to think about is having this same conversation in another 50 years and having people talk about what that was like on Mars. And I think that we're going in that direction. So learning all these amazing lessons from people that have walked on the moon, people that are teaching people how to walk on the moon. And I think the vision is so grand that it's really, really incredible.
Great. Another question.
Hi, right here. Brad Bailey, Survey, soon to be headquarters. Soon to be. I got a couple questions, perhaps, revolving around technology. And so when you were on the moon, Jack, you had a rock hammer, and some of the most valuable samples came from the rake. Are there any current day technologies that you felt would have enabled you to take better samples or recognize different terrains in a more enlightened fashion? And the continuation to that question goes to the present and future lunar geologists on the panel. What new technologies do you think we should be investing in to help us do better planetary geology in total?
So the question was, what current technologies would have been helpful to have during Apollo, and what new technologies might we need as we look forward to activities on the lunar surface?
Very rapid general analysis of the composition of materials, and I mean very rapid. If it takes any time, then it's not an efficient use of the astronauts' time on the moon. Now that again assumes that we're not yet settled there and not have people who are working continuously as field geologists on the moon. We're talking about returning samples for use here on Earth, and as long as you're going to do that, any analytical work that you do on the surface is going to need to be something that's done very rapidly and very easily. Has been talk in the past of having robotic field assistants. Well, I have a feeling any robotic field assistant is going to be picked up and placed wherever the astronaut wants it to be, rather than depending on that robotic field assistant doing something that it's directed to do verbally. So I'm not a big fan of robotic field assistants. Now, if you give me a graduate student as a field assistant, then that's a little bit different. You have a little more authority, and they take some intelligence, hopefully, to the outcrop that you've directed them to. But analytical technology in the field needs to be extremely rapid and efficient and easily used to be, I think, useful. It's like an acid bottle here on Earth. The acid bottle is very easy to use. You immediately can tell dolomite from limestone from something else. That's the kind of thing you need on the moon, is an acid bottle kind of technology. Now, if you're talking about doing triage in a habitat, you're going to be there long enough to do that because you're going to collect too many samples to bring back, then you can do somewhat more leisurely analytical work in that laboratory. But out in the field, in a suit, trying to maximize the efficiency of your time away from the spacecraft or away from the habitat, I think the standard geological tools for collecting samples are going to, and of course you're taking your eyes and your brain with you. Those are very good analytical, semi-quantitative analytical tools, and have been used very good in the past during Apollo, and I think can be used very well in the future as well.
David, any thoughts?
Sure. So during Constellation, we tested some new technologies with 1, 3, 14, and 28-day long mission simulations. And we found there are some new technologies you want to utilize just routinely. We're going to drop the Newman. We're going to use digital photography. We'll have better data tracking. You saw a discussion of that both yesterday and today. But I would say, by and large, the most important capability that you can take to the moon is what we spoke about a moment ago, a well-trained astronaut. I've said this before, the best spectrometer you can ever fly is the eyes of a well-trained astronaut. They will observe things and make in real time important decisions, make adjustments to the traverse plan and collect the right samples. And I guess the other thing that I would say is that we want to be mindful that getting those samples back to Earth, we now understand how treasurable those are. We need to make sure that we have the lift capability to get those samples to the gateway so that we can bring them back to Earth. I worry that we are going to go to some interesting terrains. We're going to have sufficiently long traverses, that these very smart people, knowing what answers we want, are going to collect these samples that we desperately need to get back to Earth, and we're not going to be able to bring them back. And so, well-trained astronaut, sample return, mass capability. Jen?
Yeah, concur. You know, we have this debate a lot, you know, can you just send a robot, can it do what the human can do? And the answer is usually no. Usually you need to have the human there who can see, who can synthesize, who can take in a scene, who can make decisions. So for all these reasons, right, you need to send the people. And we're also looking at new technologies for what, you know, especially for, like Jack was saying, rapid analysis in the field. You know, so it's got to be quick. It can be quick and dirty, especially if you're high-grading samples, because time is one of your most valuable resources. So we take instruments. We have a visible near-infrared spectrometer, taking that out. We have portable X-ray fluorescence spectrometers. We have portable laser-induced breakdown spectrometers. We take these out into the field and assess them to see which ones give you the best data and the quickest, so that you can make those decisions about which sites to look at, you know, which samples to bring back, these very valuable samples when you can't bring everything. So looking at those analytical capabilities. And then also there's some really interesting new work going on, you know, in the realm of advanced technologies like virtual reality and augmented reality. You know, heads-up displays. What's useful, and is anything useful? It's really cool, but now there's research going on now just starting to get into the quantitative aspects of that. So if you have a heads-up display that's got the terrain on it, can you overlay geologic maps so you can see what the different units are that you're looking at in real time, so you can make sampling decisions? You can have, you know, you need to get from point A to point B. Maybe you deviated a little, so you need a new traverse path to get there. But you can have an AR, you know, the computer works it out for you. Okay, what is the path that'll get you from A to B using the least amount of energy, taking into account the topography you need to traverse, your metabolic rate, your consumables in your suit, and it will map that out, and you just follow that through. So there's some really interesting new technologies that we're working on, a lot of groups are working on, and field testing these to see which ones are useful, which ones are not, and what capabilities need to be developed.
Yeah.
Yes, I agree with everything that's been said. And then the other aspect of helping with the rapid analysis is being able to allow for longer duration missions and more of a continued presence. So being able to invest in technologies and infrastructure that will allow us to continue to make these measurements and these studies, I also think is really important.
Great answers. Next question. Here.
Now, this is directed to Jack Schmidt, but correct me if I'm wrong, but I heard you say you'd love for someone or appreciate someone asking you why were the specific science experiments chosen for Apollo 11, and I wanted to do a couple of derivatives of that. I gather it was 2 hours and 40 minutes time on the surface, or EVA. The time you were walking on the moon, was it a longer EVA, and did you have access to the Lunar rover vehicle? But I guess I'll go back to the first part. Why were the specific experiments chosen for Apollo 11, and then on your own experiments?
Why were the experiment packages selected for Apollo 11 and also for Apollo 17?
As we led up to the Apollo 11 mission, you have to realize that things are moving very fast. And in the middle of 1968, the lunar module was in a bit of trouble. Its test program was not going well. We had to change out the ascent engine, which had not met tests well. And George Low had the idea that we ought to take Apollo 8 around the moon to keep the momentum up. He was familiar with that, having studied it as a member of the Space Task Group while he was at NASA headquarters well before Apollo was announced. And so he sold that. And in 4 months, depending on the success of Apollo 7, which was remarkably successful for a first flight of any spacecraft or aircraft, Apollo 8 went around the moon. And that bought us time, kept the momentum up. We learned a lot operationally. Mission Control got to work in deep space and so forth. But this problem of the lunar module and the weight of the lunar module and concern about having enough hover time was putting the original Apollo lunar surface experiment package, the ALSEP, in jeopardy. And I had done, with the assistance of Don Lynn, done a couple of deployments of that. Bill Anders and I had been at the PDR for the ALSEP. It was just not something that could be deployed in a reasonable amount of time. Unfortunately, the early specifications did not take that into account. Bendix was told, give us something to do by one of the astronauts who will remain nameless, and they did. In addition, it was 300 pounds, and that was worth 3 seconds of hover time. And so it began to be pretty apparent to me, at least, that we were not going to fly the ALSEP on Apollo 11. And at the time, there was a Charlie Towns of MIT, Nobel Prize winner, was chairman of the President's Science Advisory Committee, and they had asked for a briefing by the astronauts of how NASA was going to conduct the first mission. And at the time that briefing was done, it was still considered to be a 2 EVA mission, and that the ALSEP would be deployed. But in the workup to that meeting, I was assigned to give the lunar surface portion of the briefing, and in the workup of the view graphs, I included on the last view graph an option for going with a smaller, lightweight experiment package. And I had already called Frank Press and Gene Simmons and the geophysicists of note of that time who had anything knowledge at all of the space program and the moon, and said, what do you think would be the best experiments if we never went back to the moon? That was the way I phrased the question. And unanimously they said a seismometer and a laser retroreflector. And that was what was on the view graph, and that's what Bob Gilruth said we were going to brief PSAC on. And once that was done, it was pretty clear that the ALSEP was not going to fly, but we would fly those 2 experiments along with Johannes Geiss's solar wind window shade, which didn't take much weight at all and didn't take much time to deploy. By the way, that's still about the best solar wind composition data we have today, was that solar wind.
Any other thoughts from the rest of the panel about that? No? Okay. Next, any other questions? Up in the back?
Yes.
Excuse me, Jake. One thing that I hope that story says is you've got to be flexible. These programs not only need to move quickly in order to keep the momentum up and make milestones, but you have to be flexible in the course of doing that. You can't be rigid, and the Apollo was not a rigid program. In spite of what some people may think, it was not a rigid program. It was because both at the launch vehicle level and at the spacecraft level, people were willing to not only take risks in management, but to move quickly when it was clear something had to be done.
Question?
Yeah, I have a question for Jack. So do you still recall what's the real smell on the lunar surface? Some people said it's like a gunpowder. Do you know what caused it, give you that smell? And have you smelled anything else similar on Earth as on the moon?
So the question is, do you recall the smell on the moon? And have you smelled anything like it here on Earth?
Well, you wouldn't want to smell what I smelled while I was outside the spacecraft, but inside the spacecraft, there was a unanimous conclusion among all the astronauts that I'm aware of that expressed an opinion is that lunar dust smells like spent gunpowder. And there's a good reason for that, I think. My hypothesis is that it's like activated charcoal. It takes a while, it takes some time before it starts to absorb the oxygen and moisture in the cabin atmosphere, and it is still activating your olfactory sensors as if it were activated charcoal. And eventually that smell goes away. But initially it's like spent gunpowder.
Any other questions? One up front. So this will probably be the last question. We've got about 8 minutes, so we'll take this one. And
one of the things that we all grew up using to study anything small is a microscope. And why are we so averse, or why have we not put a microscope on our spacecraft so far? Is there a reason?
So the question is that when we try to look at small things here on Earth, we use a microscope. So why do we not have microscopes on spacecraft, or did we not take them to the moon?
Go ahead.
Okay, so I'm a petrologist, so by definition, my life is centered around a microscope. But I'm also a field geologist, and it was never occurred to me to take a microscope with me into the field. There are two different aspects of conducting the science. And so when I'm traversing a terrain, whether it be volcanic or impact cratered, I am doing my field geology. I'm looking at things at one scale, trying to develop hypotheses and collect samples that I can return to the laboratory that will address the questions and test the hypotheses. And then once I get to the laboratory, yes, I want that tool, but that's not a tool that I need in the field. In fact, it would probably get in the way if it was with me in the field.
I did have a hand lens, but of course, it's a little hard to use a hand lens with a helmet, so I used it in the cabin. And in fact, between the first and second excursions, I did look at some of the basalt samples and revised my estimate of how much plagioclase was in those samples as a result. What had initially confused me on the surface, or caused a bias at least, were these little tiny impact craters we call zap pits. And they tended to over-accent the amount of plagioclase, because when they hit plagioclase, they shattered it, and it became much whiter than usual. And so my surface estimate was, as I recall, about 50% plagioclase, whereas with the hand lens I could see it was about 30%, and I think that held up in the preliminary examination. But a hand lens is very important, but it depends on where you can use it. And it may be you could engineer a low power hand lens like optics in the helmet, but I have a feeling NASA's never going to do that.
We got one, we'll have time for one more. We're going to go over here real quick if we've got the mic. Nope. Oh, sorry, Rick. I'm going to go with the next generation. I'm sorry, man.
Sorry, Rick. You're a has-been.
Sorry
I didn't
about
mean
that.
it, man. I still need you to work on those things.
So there's been a lot of talk of inspiration, and to me what I find inspiring is human experience. We've talked a lot about the science, but the human story is the value of sending people out into space is that we get the stories back. So my question is, what were your first thoughts when you stepped onto the moon? What was going through your mind? Did you have time to feel an emotion? Were you busy focusing on what was that like for you?
You want the real answer or one that... The real answer is that my first thought was don't fall. And the reason for that is my commander had somehow or another landed the front landing gear right next to a relatively smooth boulder. And when I came off, my boot slipped off that boulder because of these little tiny beads of what we now know were ash on the surface of that boulder. It was like little ball bearings. Well, fortunately, I was hanging on to the ladder at the same time and I didn't fall, but that was my first thought, okay? Now, my second thought was how familiar everything looked, because I was working around a lunar module that I was very familiar with. I'd been through test after test, vacuum chamber, you name it, with this lunar module, and my vision right now was occupied by the Challenger, by the lunar module. And for the next several minutes, probably 5 or 10 minutes, the things we were doing were right there around the lunar module, including the deployment of the lunar rover, which happened fairly early on the first excursion. And it wasn't until one of my tasks was at the beginning of each excursion, each EVA, I went out at three corners, so to speak, of the lunar module and took a panorama. And that was the first time with a Hasselblad camera, that was the first time I had a chance to really see the Challenger in the context of this deep mountain valley we had landed in. The valley's deeper than the Grand Canyon. Mountains to the north were 5,000 feet high, mountains to the south 7,000 feet high, and really a magnificent place to be, brilliantly illuminated by a sun as bright as any New Mexico sun I had ever seen, and but also set against a blacker than black sky. That's probably the hardest thing to get used to when you're on the moon, at least for me, was the sky. The sun was bright, the sky was black. And then finally, you happen to look up high enough over the South Massif, over the 7,000-foot mountain, and there's the Earth. Only 250,000 miles away. Hey, there's home. And anytime you want to see home, all you have to do is look over the South Massif. It was quite an experience, believe me.
So that about wraps it up. I have a couple quick thoughts at the end here. Listening to the conversation and discussion here, I think it's very clear how valuable the samples we brought back, the thoughts we brought back, the memories we brought back from the moon have been to the science community. So I think we need to thank the Hornet staff and the Hornet crew who were there that day 50 years ago for really setting the tone for analyses in the future. Jack?
I happened to just glance over here, and there's the shield of the USS Ticonderoga. That was the Apollo 17's recovery ship, and as you probably gathered listening to that outstanding panel we had earlier, the decision on what recovered a particular mission was pretty much ad hoc depending on what carrier was available. And there's a long history of why the Tycho was available, but it is really interesting, and I couldn't resist looking over that half fuselage there and to see the Tycho emblem up above it. Sorry, Jake.
So cheers also to the Tycho. Thanks to the Hornet. I also think we would be a little remiss not to remember a few other folks. When I first joined NASA, my first day, I was told very clearly one of my jobs was to learn as much as I could from those who were still remaining from Apollo. I've been at NASA for 13 years, and there aren't too many of those folks still working for NASA, and many of them are not with us at all anymore. And I can only imagine from Jack's perspective what that's like. So I think we should also at least acknowledge the memories and thoughts and voices that we could not invite to these activities over the last week, because there are some important ones. So
Absent friends.
So we'll bring Greg back up. I just wanted to say it's been an honor for me to be up here with this panel of some of the best scientists we have working on lunar science. So thank you all very much.
Thank you, Jake.
Thanks, Jake. That was great. Thanks, Jake. Thanks, David. Yeah. Thanks very much, Jake, and thanks to all of our panelists. I think that was just fantastic. I learned a lot myself, and I hope you did as well. So our next event is a little bit of a surprise. It's not on the agenda, but I think you're going to enjoy it. Let me start off by asking Ben to come up here. And Mike and Laura, would you mind coming up on stage as well? So how many here have seen the movie Apollo 11? Yeah, I mean, right? This is the right audience for that. Absolutely stunning. We have here Ben Feist, who was one of the producers of this movie, and who, yeah. And in the production of this movie, came across a lot of very interesting material. And so he's going to tell you about something very special that he found. So Ben, please.
Thank you very much. Hi, everybody. It's a great honor to be standing here on behalf of the rest of the film team that made Apollo 11. As part of the effort for that film, there was a huge amount of archival research conducted, and part of that was not only the stunning footage that will be later donated to the Hornet Museum, but we also came across thousands of hours of audio recorded in mission control. And this audio has not been heard for 50 years, and a lot of it was used to bring sound back to the silent footage that was filmed during Apollo for that film. As part of that, there are 4 channels of audio that was about recovery operations that centered around the USS Hornet. And I have restored that audio, and there's 1,000 hours of it on this tiny little flash drive. Much smaller than the original tapes that were in the National Archives that we found. And today I'm donating this to the Hornet Museum as something that has not been heard. There's family calls that were made home by the family members. There was lots of, obviously, coordination for recovery and discussions around quarantine and things that have never been heard. And it's like a window being opened into the past. I believe we have a short clip that we could play right now of some of that audio.
Houston recovery, Hornet recovery. I read you loud and clear. Have you confirmed command module, service module separation? Over.
Roger, Hornet recovery. We confirmed that approximately 10 minutes ago. Passed it out to Mel. Over.
Roger, understand. I'm up on the ship's bridge right now. I just finished briefing the president, and he's out on the port wing of the flag bridge immediately below me here. It looks like it's pretty well clobbered up out here. I doubt very much if we get to see anything. So our sea state and winds are not bad. It's simply the high cloud cover, and I doubt that we're going to get to see anything. Over.
Roger, understand.
So there's a lot more of that. If you're interested in hearing it yourself, you can hear it at a website called apolloinrealtime.org, where it's all locked to mission time. Thank you.
On behalf of the Board of Trustees and the staff, Laura, who runs the museum, basically. She keeps me on time. She's our curator, makes sure all these collections go through. This will be put to very good use, and we're very honored to accept this. And it's been a great pleasure for us, for me, the kid who used to watch the launches at ODARC 30, my dad would get me to watch them. It's been a great treat to see Harrison Schmidt and other people here. So thanks for making us part of your day. We really enjoyed it. Thank you.
Thanks so much. This is what a pleasure. So the concluding part of our program, our NASA program today, for this concluding part, we're going to have leaders at NASA talk about not only a look in the past, but a look forward as well. You've all heard that we're returning to the moon, or as we like to say at NASA, we're going forward to the moon. So I'd like to introduce some very special people who are here with us today who'd like to share the plans. And so I'm going to introduce them. I'll ask a couple of questions, but we really want to get all of you engaged as well. So immediately to my left, you've already met Dr. Jake Glick. Jake, like I mentioned earlier, is the Chief Scientist for NASA's Human Exploration and Operations Mission Directorate. He's a volcanologist and a field geologist. He has also been a part of my institute, SURVEY, since, I think, pretty much since its inception. So he represents the human exploration side of the house. To Jake's left is Dr. Lori Glaze. Lori is the head of the Planetary Science Division at NASA headquarters, part of the Science Mission Directorate. She is a planetary scientist herself, with an abiding interest in Venus. But now it's all the planets are equal. And she's in charge of a lot of super cool things like the Juno spacecraft to Jupiter, all the Mars spacecraft that you see, etc. She has the keys to all of those. To Lori's left is Mr. Steve Clark. Steve is the head of a new program at NASA, the Lunar Discovery and Exploration Program. He's also Deputy Associate Administrator for the Science Mission Directorate. He is a former director as well of the Heliophysics Division at NASA headquarters. So please welcome our distinguished guests. And so, like I mentioned, I have two questions I'm going to ask each of our guests. I'm going to start with a look towards the past, and I'll start with Jake here. Jake, how did Apollo and the other missions that you saw in your youth, how did they inspire you, and how did they shape your career path?
So I've had to think about that a lot over the last week. I've been on a lot of interviews and talking with folks on the radio, and we go through, when you're in positions like we are, we go through media training, and we learn that you need to have a key message you want to get through. And it's nice to have a good one-liner. And my good one-liner for this whole thing was, as we go forward to the moon, we're standing on the shoulders of Apollo. And there's no way that we are going there without carrying with us the knowledge, the experiences that Apollo gained for us. And by the way, I was texting with Ben Feist here and our pal Noah Petro about this, and he said, well, I'm going to start using that line. So if you hear him say that, it's my line. Boom goes the dynamite, Noah. But that is actually comes from a Isaac Newton comment about if I've seen further, it's because I stood on the shoulders of giants. And there's no other way to really think about this. We're going to the moon by 2024. We're going to land, first woman and the next man at the south pole of the moon. But we're not doing that in isolation. We are doing it because of all of the space science research that we've done to get to this point. We learned the lessons about how to land robots, how to land people, how to conduct operations on the surface. So none of that's possible without this. I was talking to a few of the folks who talked 2 panels before us that were actually on the Hornet. The gentleman made a comment about how it was kind of annoying to him as a 22-year-old that he wasn't getting leave, he had to be here. And I said, well, look, I'm going to do everything I can to make sure we frustrate some 22-year-olds in the future as we're going back to the moon, this time in a sustainable way.
Thanks, Jake. Lori, please.
Yeah, so, on? Is this on? Yes. So I thought I would just share a little bit of my personal inspiration story, which, when Apollo flew and when they splashed down in 1969, I was around, I was alive, but not quite at a point where I was really coherent of what was going on. So while it certainly inspired me later on in my life, what really inspired me, I wanted to carry beyond just the lunar exploration program, which is why we're here today, but into additional human exploration that occurred beyond that, which is through the space shuttle program and onto the International Space Station. And in my personal story, both of my parents were engineers and both worked on different aspects of the space shuttle program, developing and working on different aspects of that space shuttle design. And to me, as a young woman growing up in junior high and high school, that was an absolutely inspirational time for me to be able to see that we were enabling a new type of human exploration. At that time, we weren't sending humans up, and we were able to send them back through the space shuttle program. And to me, that was hugely inspirational. Of course, they were both engineers, and I grew up and said engineering was not for me. I had to do something different to break the mold. So I went into a new career field that you heard David Kring talking about earlier, that during the time of the Apollo program, when the first Apollo 11 landed on the moon, there was no such thing as planetary science. The way we looked at planets was through telescopes from Earth. It was called astronomy. But with the landing on the moon, that opened up a brand new field. It actually invented the field of planetary science, where we actually now think of actually visiting different destinations in the solar system and conducting science at those locations, and that is in fact planetary science. And the lunar missions, Apollo 11 and beyond, with the samples that they brought back, as Jack was saying earlier, essentially gave us that fundamental information about how the solar system formed and evolved, that earliest part of solar system formation, the early bombardment, the way that planets came together through accretion and then were modified through additional meteor impacts, informed us about how the solar system formed and inspired us and encouraged us to explore beyond the moon and go into the rest of the solar system. And as Greg just said, I'm absolutely honored to have the ability now to work in a planetary science division that has missions spread across the entire solar system. We have missions at the moon, of course. We've had recently missions at Mercury. We now have missions all the way across the solar system, many at Mars, missions at Jupiter. We have missions all the way out into the Kuiper Belt, beyond Pluto, and we're planning new missions today that will go to new destinations and have new discoveries as we go forward. So as we look back at all of the incredible discoveries that were made 50 years ago, we're ready now to move forward with a new generation of scientists and engineers for that exploration as we go into in the future of the unknown. So thank you.
That's cool. Thank you. It's amazing how far we've come. Yeah. Steve?
Well, it's obvious that I'm the old man of the group because I was alive and I remember it well. On July 20th, 1969, I was 9 years old, sitting in front of a black and white TV in my grandparents' living room with my sister, mother, and father, and watching it live. I had had some inspiration leading up to that point. My dad was an Air Force pilot, so I grew up around airplanes. And he used to have Aviation Week in Space Technology magazine come to the house. And, you know, as I was younger, I certainly didn't understand what I was reading, but I was looking at the pictures, and I saw the Gemini missions unfold in front of me, and the astronauts, and leading up through Apollo 8, of course, you know, going around the moon. So leading up to that morning, or that day of July 20th, I looked over at my dad, and my dad was West Point grad, tough as nails, never showed emotion. Tears came out of his eyes watching Neil Armstrong going on the moon, because he just could not believe we were actually doing it. And between his reaction and me watching it, I knew that I wanted a career in either aerospace or, you know, flying airplanes or being involved in the space program. And so, unfortunately, my eyes went bad when I was young, so I knew I wasn't going to be an Air Force pilot and follow my dad's footsteps. But I wanted to get involved in the space program, and I felt honored to actually have the opportunity to start working on the space shuttle program. That's where I started my career. I was saddened to see Apollo didn't continue, because I thought, hey, we're going to just keep going back to the moon and on to Mars, and by the time I graduate and get my degree, we're going to be out there all over the solar system. But obviously that didn't happen, and you know, you heard Jack Schmidt say earlier, stay flexible. Well, that is definitely a key, going through all the different programs and fits and starts, but Space Shuttle program, International Space Station, Constellation program, David talked about that, lived through that. You just got to stay flexible, and now here we are, and I'm in a position now working with these folks here and others to actually make this happen, to return humans to the moon by 2024, science being the primary driver of the reason we're going back. Not a second thought, not an afterthought, but a primary driver. And I'm actually seeing a good intersection between science, human exploration goals, and technology development. I've seen a synergy now at NASA that I haven't seen before to this level. And we're working very closely together to make the first human return mission happen. But we're also looking at doing something different. And I'm in charge of a program called the Commercial Lunar Payload Services. We have commercial companies that are developing landers to take NASA instruments and other customers' payloads to the surface of the moon. And NASA is actually buying a ride. We're not managing the mission. We're not in charge of the mission. We don't own the hardware. We're buying a ride. It's almost like a FedEx or DHL service to the moon. And it's a brand new way of doing things. And I think it's going to be successful. And it's just the start of how we are working closely with our commercial partners. We're going to be doing that in the human spaceflight side too. This is really a new era of how we're going to do space travel. So I remain inspired, and I hope everyone out there is inspired, because the way we return to the moon is going to be different. But we are leveraging what we have certainly learned from Apollo and what we've learned from our long stays at the International Space Station as well.
Thank you, Steve. It reminds me of that scene in 2001, A Space Odyssey, when the Pan Am spacecraft is coming up to meet the space station. It took a little bit longer, but I think that's the direction we're going. I wanted to share a little story myself. Steve and I found out earlier today that we were both 9 years old when the landing happened, and I actually found something. My mother told me that she had something she wanted to show me a few years back, and when I got over there, she showed me a little drawing, and what the drawing said, it was just done when I was about 6 or so, and it showed a picture of some spacecraft, and it said, when I grow up, I want to work for NASA. And so that was really weird. Been there 34 years now, but it's an illustration of what Jake talked about earlier about the inspiration. You know, I was inspired by Mercury and Gemini, and then Apollo. It's done so much, even for kids that don't end up going to the space program, to bring them into STEM fields. So what I'd like to do now is I have one more question for the panelists, and that's, what are you doing now, you and your organization, to advance our return to the moon. And for this one, I'd like to start with Lori, please.
Great, thank you. So I think Steve just mentioned a minute ago that the importance of the difference in how we're going about returning to the moon this time and thinking forward to going to Mars. And one of the key parts of that, of course, is that the science is driving exploration, and then the exploration component is enabling more science. And there's a bug here, sorry about that. But they're working together hand in hand, as Steve says, from the outset, really thinking and working together about how we can get the most out of a new human exploration program to push more science, to get more science, enable more science, and then use that science to, again, enable more human exploration. So within our division, within planetary science, we're focused on the lunar science that we can do in the immediate future, and developing new instrumentation and thinking about what types of science do we want to do. We're working with the survey forum that Greg leads in order to better understand the types of places we might go and what types of science can be done there, thinking about what collections of instruments might really do some fantastic science on the surface of the moon. But we're also thinking ahead within Planetary Science Division, thinking about the next step, which is going on to Mars. And we don't ever want to lose sight of that when we're talking about this exploration program that we have now, it's Moon to Mars. We're thinking about going to Moon and then on to Mars with humans. And so a lot of the robotic exploration that we have going on at Mars right now is helping to pave the way for that future human exploration. We're not only learning more and more about the surface environment on Mars, we're trying to characterize what it's like, understanding what types of, again, potential resources. You've heard Jen Heldmann talk a lot about the water that's present on the moon. We also want to understand the distribution of water that's present on Mars, so that we have those resources to work with. We're also now in the process of planning the first Mars sample return mission, the first time we will ever bring a sample back from the surface of Mars. And through that process, we'll have to learn how and demonstrate the ability to launch from the surface of Mars. So again, thinking and planning ahead towards future human exploration, we're trying to lay that framework and lay the groundwork so that when human exploration is ready to move beyond the moon, we've got that foundation ready to go.
Great. Steve, I know you started to answer that question, but do you have anything else to add?
So talking about the commercial lunar payload services again, we've already awarded the first delivery services to 3 companies. And we're going to be flying as early as late next year and into 2021. And we've already selected the instruments and the technology demonstration payloads that are going to go. So we're off and running with our commercial partners to get this started. And our plan is to fly 2 delivery services missions per year. We're also excited about the fact we are developing a rover that we want to fly to the South Pole at the end of 2022 because mobility is going to be a key asset for science, because it'll enable us to go to many locations and take many measurements and data points within the range of the rover. And in fact, this one, we call it Viper, is going to start doing what we call the ground truth of the volatiles in the South Pole region. Because as Lori mentioned, we're interested in the ice, the water ice that we know is there. Now we need to start going and touching it, right, robotically, and finding out what's the distribution of that water ice. How much of it is it there? And we need to go to several locations, not just one location, to do this ground truth. Because eventually, once we've characterized how much is actually there, then we need to find out how easy or hard is it going to be to excavate that water ice. And you heard on the previous panel about the ability to break the water into hydrogen and oxygen and also use it for drinking water. That'll be the next step. We need to understand how much we can excavate and how can we do that in quantity sufficient to basically support humans on the surface of the moon in a sustainable way. So we've got a lot in the pipeline. When we say we're going back to the moon from a robotic standpoint, we have missions on the manifest. We're working with our commercial partners to make it happen. And so I'd encourage you to stay tuned, because you're going to start seeing more and more of this ramp up here over the next couple of years. I'd also like to add, working with the human spaceflight side, we're actually started working on the first science plan for that mission in 2024. Because we need to start working out what kind of science we would like the crew to accomplish on that mission, and then lay out what instruments are we going to take, right? So that's got to start now. We're less than, 4.5 years away, right? So the clock's ticking. And so we're working with our human spaceflight colleagues to work out what kind of science we want to do on that mission. Astronaut training will come into play as well. Jack Schmidt talked a lot about that, right? So training is key. So all of this is going on now. So we are working till 10 o'clock at night a lot too, Jack, actually, and on weekends. And with the technology today, with email and phones, it's 24/7 pretty much. So all hands on deck.
Thanks, Steve. Appreciate that. So Jake, I wonder if you could share some about our human return to the moon in 2024.
Absolutely. So within human exploration and operations, I work in the Advanced Exploration Systems Division. So we're really focused on that next generation of systems that's going to enable us to push out to explore new areas. And in this case, that means the lunar surface, and as Lori mentioned, preparing for surviving in deep space and eventually sending humans onto Mars. So we really have this long-term goal that's driving our return to the moon right now. So the systems that we are developing are actually not all that different from during the Apollo mission. We have two major systems. One is called the Gateway, and one is called the Human Landing System. And so like during Apollo, the crew were launched, and then there was a separation in lunar orbit of the command module and the lunar module. One crew member stayed in orbit while two crew members descended to the lunar surface. In the case of exploring the moon for 2024, we have the Gateway, which will be basically a destination that the Orion capsule can deliver the crew to. The Gateway will remain in orbit around the moon. It's in an orbit called a near rectilinear halo orbit. It's a lot of words. What that means is this orbit goes around the moon basically in a polar orbit, but it goes out to about 70,000 kilometers. So that will enable us to do research, conduct research that helps us better understand the space environment that we will have to deal with as we move on to Mars. In addition to that, the human landing system itself can go to the Gateway. We need to launch, we believe, 3 separate elements: a transfer element, a descent element, and an ascent element. These elements together make up the human landing system, but they each need to be launched on a separate rocket to get to the Gateway. So instead of having these spacecraft sitting out in deep space on their own, which means you have to design them to support themselves in deep space, they'll dock with the Gateway, and that's where they'll aggregate into the human landing system. So the Gateway itself will not only provide support to the humans who are in orbit around the moon, but to the human landing system until it's ready and the crew are delivered for them to descend to the lunar surface. So it's almost like the Gateway is our command module. We have crew members initially that will stay at the Gateway. We believe 2 of our 4 crew members that the Orion can deliver to Gateway will stay on the Gateway. 2 crew members, at least initially on that 2024 mission, will descend to the surface. So we've been told we will land humans by 2024 in the south polar region of the moon. The orbit that we have for the Gateway enables that to happen. So the crew members that go to the surface, the astronauts that go to the surface, first woman to the moon, next man to the moon, they will descend to the surface in the human landing system. The transfer element will carry it to low lunar orbit. Crew members will then descend to the surface while riding in the ascent element, which means that the crew members actually only reside in the ascent element. So that means that we only need the human ratings for that one element. We don't have to over-design all of the system to support the people. So we can put that on the ascent element. The descent element will take us to the surface. From there, our crew members can conduct surface activities and research. Then they'll return. They'll go back to the Gateway on the ascent element. Then they can return to the Orion once they're reunited with the other 2 crew members and come back to the Earth. and hopefully be picked up by a wonderful ship like the Hornet here, or Tycho that picked Jack up. So that's the plan right now, and I will point out that this is the NASA design concept study, but we're working, as Steve mentioned, with our commercial partners, and we're looking to them to help us reach these goals. So it may very well be that they have some slightly different designs. So we just want to be very clear, that's our design concept, but we're working in partnership with the commercial partners. Once we get to the lunar surface, we believe we'll be partnering with our international partners as well a good bit. 2024 is that first goal, getting humans back to the moon. But beyond 2024, we're hoping to develop a sustainable presence. So that means we'll be delivering hardware to the surface, maybe habitats, maybe roving vehicles, other instruments, tools, science packages, in collaboration with our Science Mission Directorate. So my job really is to look across this whole plan from the Human Exploration Group and to ensure that the opportunities are present to enable us to do the science that we work on with the Science Mission Directorate. So it's kind of where we stand right now.
Thanks very much, Jake. I hope that those of you from the public are seeing that we're doing this in a different way. The key word here is sustainable. We're involving commercial partners. We're also involving international partners in a major way in construction of the gateway and other things that we're doing. So it's a really different approach than what we did in the 60s leading to Apollo. So now I'd like to open it up for questions, and I want to have a little incentive for any members of the public here. If you ask a question, you get a NASA pin. Anyway,
that counts survey team members. Get down to one to do whatever.
We can all have NASA pins. So I don't know where the mic is.
Hold on just a second. I'm seeing if there's questions here. Questions.
Where do we have the roving mic? Here it comes. Oh, okay.
I'll get started here and we'll move down. Can I see your hand? Okay.
Hi. In light of today's Robert Mueller testimony, I was wondering about Russia. Is Russia one of the partners internationally that you're cooperating with on this venture?
So we certainly partner with Russia on getting to the International Space Station. They've been a dependable partner for us. They've been delivering our crew members to the ISS, International Space Station, via their Soyuz capsule. We're talking to all of our international partners right now, which includes Russia, but they also have their own plans for exploring the lunar surface as well. So, we are meeting routinely with partners, including the Canadian Space Agency, European Space Agency, JAXA, some of the individual nations as well. That is not my job per se, but I would say that we are looking for a way to establish a sustainable presence on the lunar surface for humankind. And so NASA will continue to push forward to the new frontier. And so when I say that we're going to the moon, we want to go to the moon, do the science we'd like to do, establish that sustainable presence, and then move on to explore and deliver humans to Mars. And so I believe that partnerships will continue to be looked at for how that will be enabled.
I'd like to add to that, and I'm sure Steve will add to this as well, but this is another area and another way in which returning to the moon in this era differs from going to the moon the first time in the late 1960s and early 70s. Is that at this time there are now a fairly substantial number of spacefaring nations that have a very keen interest in getting to the moon. And you mentioned Russia. Russia has a really extensive program planned to send multiple missions to the moon. Europe is planning a mission to the moon. The Japanese are planning a mission to the moon. The Indian Space Agency just launched a mission to the moon that'll be landing in a couple months. So they're on their way. Israel recently, a privately funded company, organization within Israel, successfully launched and delivered a lander to the moon almost landed softly, landed a little harder than they intended. But the Koreans South Koreans have a polar orbiter that they're going to be sending to the moon. So we're now talking about, when people start talking about a lunar village and the ability to really enable substantial science and exploration at the moon, we're not doing it alone. We're doing it in partnerships and in collaboration with an entire international community. And I forgot to mention China, which has actually now successfully landed on the moon a couple of times in recent years, and they also have an extensive program to land on the moon. They recently landed on the far side and have successfully delivered a rover that has been driving around there. So this is really an exciting time for lunar exploration, and Steve can add a lot to that, I'm sure.
Well, the only thing, good discussion here, I think that what I'd add is, like on the Indian Space Research Organization mission that just launched, we are flying a laser retroreflector assembly on there. On the Israeli lander, we had one on there as well. We have been talking with JAXA about flying that also on the JAXA lander. So the purpose there is it doesn't require power, and it's very lightweight, and it's basically, we want to put one of these on any lander that goes to the surface of the moon, because it basically starts setting up a geolocation network for future landers for navigation purposes. Because you could then laze from another lander coming in and start determining exactly where you're at and feed that into the navigation system. So we've already started these partnerships because now we've already contributed some NASA instruments to those landers, and we're in discussions with our international partners of them providing instruments that we will fly on those commercial lunar payload services missions as well. Certainly, as Lori said, the Russian Space Agency has their plans, and we have been talking. Lori's been talking more so from a science standpoint, but we're open to talking to collaboration activities, not just with them, but all of our international partners, because this really is going to be a global effort from a science standpoint. It's not going to be just the U.S. Certainly we'll start out with U.S. human astronauts going to the surface, but from a science standpoint, we are utilizing a lot of the relationships we've already built and leveraging those, and we're building new ones as well. So very exciting time with the international partnerships as well.
And I think one last key aspect to that is that, beginning of this calendar year, this wasn't the goal that we had before us. So we are all on the international front right now trying to understand everyone else's goals and plans and hopes for the lunar surface. So we're very much in a fluid conversation stage, I would call that. And I think what we'll see is that there will be obvious overlaps. And then as we identify those overlaps based on the planning we're doing now, that's where we can start really talking about how to collaborate towards the goal Lori mentioned about, multiple nations on the lunar surface.
Yeah, I'd like to add one thing as well. First of all, with Survey, international partnerships are really a core part of our institute. And Lori mentioned the launch of Chandrayaan-2, but I really wanted to highlight as well Chandrayaan-1. And in the audience is Carly Peters over there, who was one of the principal people that discovered water on the moon. Would you mind raising your hand, Carly? Yeah, and that was an international collaboration. She had an instrument aboard Chandrayaan-1. So next question, Penny Boston?
Had his hand up. Thanks. So, thinking about the human exploration end of things, what are we going to do about suits? Because, moving up our human landing aspirational goals from 28 to 24, as we all know, is putting us on a very tight schedule. The Apollo-style suits were nothing if not cumbersome, and presumably we're going to ask our people on the surface to do significantly more rigorous activities on behalf of science and operations in general. So I'm worried about suits. I had a long talk with Stan Love at Johnson, who's of course one of the astronauts, about his concerns about suits. Plenty of people who are going to have to be wearing them on the moon are concerned about this. So do we see a ramp up in trying to get suits ready for this very compressed time frame?
Yeah, that's a great question, which is about suit design and are we going to be able to have a new suit design in place for 2024? And so first I'll answer at a very high level that we're looking at all these systems that way. I mean, we have to design systems to enable us to get to the surface by the end of 2024. Now we refer to that as phase 1 right now, which is landing in 2024. Phase 2 is building towards a sustainable presence on the moon. We recognize that the systems we need to build to make the phase 1 goal are not likely to all carry forward completely through into phase 2. So there is likely to be some aspects and suits, the reason I wanted to explain that is that suits are likely to be one of these things where we are designing a suit to enable a landing for 2024. Some aspects of that may move forward into a more sustainable and evolvable design that can support that longer stays on the surface. But many of our systems are going to be designed that way. To land on the surface of the moon by 2024, we probably are not going to have full reusability of many of the systems that we are expecting to evolve into a reusable and sustainable system later. So right now we do have plans for developing a 2024 suit, and we're moving forward on that. And the astronauts, as always with anything that they're going to be involved in riding on or fitting inside of or using, they have a good bit of input into how that's going to go.
Great. 2 more questions. So one right there, Bob.
Thank you for your panel, this panel, and your perspective. My question is also about sustainability, scaling, and pace. So once we get out to 2028, do you still see reusing the same ascent, descent, and transit vehicles, or is this a whole new set of launch vehicles? And what's the current thinking towards beyond 2028 to when we can establish something that looks like a permanent outpost on the surface, that even if it's not staffed full-time, that they're returning to it and it's an instrument base?
So I'll answer that question. I'm sure that you may all have some thoughts about that as well. Moving out into that phase 2 design, one thing I want to be very clear about is that we expect to be slowly building up assets, collecting science data along the way that help us understand the environment that we're going to be designing to survive in. So it may very well be that we have to over-design to survive in 2024, but as we learn the lessons from the instrumentation, the science communities telling us what that environment is like, we can start to fine-tune the way we're building it. The other critical part to the sustainable phase out to 2028 and beyond is the partnerships that we're going to develop. So, NASA is not envisioning building all of this hardware in isolation of all others. So the question about international participation is a critical one. So we expect that, and from these early discussions, we see that there's a lot of interest to be on the lunar surface. So we're talking about a slow build-up, slow evolution of the systems that initially get us there in 2024. The current concept that we have in place is that that 3-element human landing system study that we have, that the ascent module and the transfer element potentially should develop into reusability. That means we'll have to be testing things like refueling at the gateway. If we can access resources on the surface and use them to help with that, that will be critical. We can test a lot of these things at the International Space Station right now, refueling, reusability. So it really is a complete system from ISS, testing on the ground, the whole way through to the lunar surface, which then itself becomes a test bed for learning how we go onto Mars. And the key to that is the kind of data that we're going to be collecting, because the Human Exploration Operations Mission Directorate really needs that information to help us survive. So it's science value, but it's also kind of an applied science that helps us better design for that sustainable phase later.
I guess pulling on what Jake said too, from a sustainability standpoint, I'll kind of look at it 2 different ways. Robotically, doing science, I think that's long-term sustainability, no question. And particularly if the CLIPS approach is a success and we're able to buy rides to the lunar surface, a couple times a year and go all over, far side, both poles, different areas to do science, I think that is a no-brainer. I think we're going to do that. From a human standpoint, pulling on what Jake said, we have to do that ground truth that I mentioned. We have to see, can we actually execute ISRU, in situ resource utilization, on the moon? And we're going to find out as we go along. If, for instance, we find that it's extremely difficult or it isn't as viable as we thought, we may pivot, right? We may not set up a permanent location. We may do more of a field station concept as we're testing systems to go to Mars. We just don't know right now. We need to learn along the way and learn what we do as we go. We need to get there and get the data to start informing what we want to do from a long-term sustainability standpoint, from a human exploration standpoint on the moon. But again, robotically, I think we're going to be doing long-term science investigations on the surface and in orbit for a very long time.
They've covered everything. I'm gonna we can take another question.
All right, great. Let's do one last question. There's someone in the back there wearing a hat. Gentleman in the hat.
Sir. The question is, at what point are you going to be changing the type of propulsion systems? Because right now I think we're still in the Stone Age. If you want to go way out, even to Mars, you're going to have to get a better propulsion than we have now. It just takes too long to get there. What are your aspects to getting that done? Are there things in the works, or are they still not really there yet?
So I'll start, Jake can jump in. Our Space Technology Mission Directorate has been doing a lot of work in that area. We are looking at solar electric propulsion. We're looking at solar electric propulsion chemical hybrids. We're looking at nuclear thermal. So we are looking at a lot of different alternative propulsion concepts to do the deep space exploration for the long term. That's active now. For instance, and Jake will probably tell you more about it for the Gateway, the power and propulsion element, which is the very first key element that got awarded, is solar electric propulsion. It's not the typical chemical locked hydrogen type system. One of the CLIPS providers, one of the commercial companies that we awarded a delivery task order in the July 2021 timeframe, 2 years from now, they have a liquid oxygen methane propulsion system, which is going to be really the first locked methane system that'll be tested with a lander on the moon. That has shown great promise as well from a propulsion standpoint. So we have started developing new propulsion systems, and we're studying others to actually be able to take us out farther and cut down the amount of travel time for crews as well.
And, that is exactly what we're doing. We have the Space Technology Mission Directorate is investigating that for us. We're trying to do technology demos and investigate new methods of propulsion. That said, Mars is very far away, and that is why we're using the moon and the lunar orbit as a place to begin testing and learning how to survive in deep space, because we can't just make Mars closer, and it is going to be really hard to develop those systems that get us there significantly faster. So we need to understand that space environment. We need to understand how to live out there. We need to understand how crews will operate somewhat autonomously without direct interaction on a near real-time loop with folks here on the Earth. And so these are all things that we're testing, as I mentioned before, from ground tests to ISS, eventually to Gateway as we get there on the lunar surface. We are actively considering how we use all of these as analogs for going onto Mars. So it's kind of interesting, the moon is a scientific, exciting target in its own right, but in some regards it's also considered an analog for us in preparing to get to Mars from an operational standpoint. It's a lot easier to test those things here in the lunar system than it is to just jump straight to Mars and try to figure it out on the way. So at the same time as we work on developing the new technologies that will enable us to maybe go faster, We have to also develop develop the systems based on our understanding of that environment to help protect and enable our crews to survive that trip to Mars.
Yeah, and I'll just say a small, couple of words here, and just to concur with Jake, that yes, we need to develop the new technologies to try and go faster than we are now, but ultimately it is still going to be a long trip, and we can't change the light delay time for communications, and so those challenges will remain. And so, as Jake says, the demonstration of the capabilities at the moon are really going to help us in preparing for sending humans to deeper space. So that's got to be the critical part.
Great, great. Well, thank you all so much. I appreciate everyone staying and listening. I hope you've gotten a really clear message. NASA is really serious about this. We want to go back to the moon. We want to go to all these other destinations. We're doing it in a different way. I'm as optimistic as I've ever been about our future. It's just awesome. So could we please thank our panelists? And to paraphrase Buzz Lightyear, to the moon and beyond. Thank you.